Okay, so we're just looking at this part 4 of the probability and statistics unit, and this section is looking at something called statistical inference, or populations and samples. And I guess the context of what we're working with here are looking at things like when you take surveys, it might be a census, or it might be just taking a sample and conducting a census, really looking at a particular characteristic in something. So for example, maybe we're looking at studying the number of people in a population or in a sample who have blue eyes, as an example. Okay, or maybe looking at, as it says here, the IQ scores. So when we're looking at a population, that's talking about the entire group of people. So not necessarily the whole population of the country, though that may be an example. It might be, in this case, the whole of the Year 12 students. Okay, that would be the population. Whereas if you only looked at a class of Year 12 students, then that would be a sample. Okay, when we're dealing with a population that's not practical, so it's too large, or perhaps it's difficult to access, or maybe in this case the data collection process is destructive, then we take a sample to be representative of the population. So that valid conclusions about a population can be made from a sample, the sample must be representative of the population as a whole. That's always the aim when you're taking a sample. If we're interested in certain characteristics within the population, and in particular the proportion of the population with a particular characteristic, then this is called the population proportion. So population proportion is represented by the lowercase p, and that is found by looking at the number within the population that has the characteristic, divide that by the population size. That's fairly kind of logical, I would think. The proportion of a sample with a particular characteristic, okay, the proportion of a sample with the particular characteristic is called the sample proportion, and the notation we use for that is the same, lowercase p, but it has this little funny looking arrow thing on top, or a hat. We just call it p hat. Okay, so that's referring to the sample proportion, and so found in a similar way, the number in the sample with the characteristic divided by the sample size. Now we'll note here that there is a difference between the two proportions. The population proportion is unchanged, okay, because it takes the proportion within, or the quantity with the characteristic within the entire population. It's going to be constant, okay, and as such it's called a population parameter. Okay, all right, so that is distinct from a sample statistic, okay, which is what p hat is, the sample proportion, and for each sample you take, it's going to vary somewhat. Okay, and that's the crux really of what we're working with in this particular section or part of this unit on probability, okay, is the fact that p hat will vary from sample to sample. Okay, let's look particularly at the sample proportion. In most circumstances, when we select a sample, it is from a population that's very large. Okay, in this situation, it's fair to say that the probability of observing a particular characteristic will remain with each selection. Okay, so the probability that we're going to get the sample proportion is going to be the same every time we take the sample. It doesn't mean the result will always be the same, but the probability is the same. Okay, so what we can do then is we can assume that each sample selected is going to be independent. Okay, and so with that in mind, we can also use our knowledge of the binomial distributions to calculate associated probabilities with for each possible value of the sample proportion. Okay, now this here is this p hat equals x over n, given on your information sheet. Go to the last page here, and you can see here it is here, p hat equals x over n. The x represents the number or the quantity within the sample that has a particular characteristic or attribute, and n is the sample size. So let's look particularly at this first example. It says here that it is known that 70% of all 17-year-olds in Australia attend school, and a random sample of 4 is selected. So it says here that it's known. We would say then that is the population proportion P. Okay. What we want to do here is complete a distribution table that shows the possible number of 17-year-olds in the sample who attend school. And that same distribution table will have the sample proportion and the respective probabilities. So, distribution table, like we've done previously in our other sections. Okay, so we're looking at the number of 17-year-olds in the sample who attend school. So then so we've got a total of 4 that we're selecting. So from that number of 4, we could potentially have 0 that attend school. We could have 1 that attends school, 2 or 3, or perhaps all 4. Okay, so that is the number that we're looking at. Okay, and so this would be x, if you like, letting x be the number of 17-year-olds who attend school. P hat then is the proportion within that sample who attend school. So in proportion, 0 out of 4, what's the proportion of that? It's 0. For 1, the proportion of 1 out of 4 is literally 1 over 4. Then this is 2 over 4 or 1 over 2. This would be 3 over 4, and this would be 4 over 4 or 1. So this is the proportion there, and then we could have it as a fraction, we can put it as a decimal, it doesn't really matter. Okay, so then what is the probability that, I guess, p hat equals p hat, so what's the probability that that's going to be the case? Well, then we need to use, as we said before, we can assume that the likelihood is going to be the same. We know that the probability of success will match the actual population proportion, which is 70% or 0.7. The number, or the sample size, is 4, so we can use binomial PDF on our calculator to actually find the values. Okay, this is our probability of success, that's our sample size, and these are our x values, and so your probability of x being these is going to be the same as the probability that your proportions is this. So probabilities, as I've worked out previously, 0.0081, 0.0756, 0.2646, 0.4116, and 0.2401. So that's our distribution table for A. Part B, then, what is the probability that in a random sample of 4 Australian 17-year-olds, the proportion attending school is less than 50%? So less than 50%, we're looking at this here, in other words, 0 or 1. Okay, and so then the probability that P hat is less than 0.5 will be the sum of those two. which is 0.0837. Okay, so that's an introductory example looking at this and sort of relating the numbers to sample proportions and so on. Okay, all right, let's keep going. Now, we're looking at the mean and the standard deviation of the sample proportion. The mean can be determined using our knowledge of expected value, and it is similar for the standard deviation. However, this may be simplified such that the mean or expected value for the sample proportion is equal to the population proportion. In other words, we would expect, okay, on average, the sample proportion to come out with the average being the actual population proportion. We know that it's highly unlikely to match that on the very first go on a particular sample. Okay, it's the probability that it will be, however, odd, so that which means that on average, over many samples, you would expect the average to come out at being matching the population proportion. The standard deviation is given by this here, the square root of p times 1 minus p divided by n. Okay, so looking at that, these are given here, your mean is given there, the standard deviation of the sample proportion is given by that. Okay, so you'll notice here, these are the different ones. So your variance, standard deviation is going to be the square root of those. So it varies a little bit to what we're doing here, but we still have this p times 1 minus p. It just varies a little bit with what we're looking at here, specifically for dealing with these statistical kind of samples and so on. All right. So let's continue with this theme of 17-year-olds in Australia attending school. If a random sample of 20 is chosen, we've still got this 70% is the population proportion. We want to find, with this random sample of 20, what is the, or we're showing that we want to find the probability that the sample proportion is equal to the population proportion. Okay, so what is the probability that our p hat will match p? So we are given here n equals 20. We're wanting to find the probability that p hat is going to equal 0.7. Now, given our sample size of 20, then, and we know that p hat is equal to x over n, then we can set 0.7, that's what we're wanting p hat to be, is equal to what number over 20? Okay, so solving for x, that gives us 14. So specifically, we're looking then at what's the probability that from this sample of 20, we will get 14 17-year-olds who attend school. So what we can do then is using our binomial distribution formula, then it's going to be 20 choose 14 times 0.7 to the power of 14 times 0.3 to the power of 6, which gives us a value of 0.1916. So around about 0.2, okay, 19%, okay, is the probability that this particular sample, or any particular sample size of 20, is going to have 14 17-year-olds who attend school. Okay, let's keep going. Part B. Find the probability that the sample proportion lies within one standard deviation of the population proportion. So then we're looking to find the probability that mu minus sigma really probably shouldn't have that there, mu plus sigma. Okay, that's what we're looking for, where mu is our mean, which is the expected value of the population proportion, which we've seen is going to be 0.7. And then, no, that is actually going to be hit, okay, because we're finding the probability that the sample proportion is within one standard deviation of the mean. Okay, what else do we know? Sigma is going to be the square root of 0.7 times 0.3 divided by our sample size of 20, which works out to be 0.1 0.025. So then we are saying, what's the probability that our p hat is between our mean minus and plus 0.1025, and that works out to be 0.5975 and 0.8025, okay, based on those two numbers. So the probability of that. Now what we need to do is, like we've done here, we relate these values here for p hat to actual x values. Okay, so by multiplying these values by 20 to find our x value, then it's actually going to be 12, or rounded to 12, it's like 11 point something or other. Okay, that's x, and that one is 16. So we need whole discrete values. Okay, so rather than putting a decimal value for x, we'll just put actual integral values, because we're dealing with numbers of people, so it needs to be a discrete value. Okay, and then we can use binomial CDF here. Okay, so we're going to go with our interactive distribution, continuous, no, discrete, binomial CDF. Our lower value is 12, our upper value is 16, number of trials is 20, probability of success 0.7, and so we get 0.7796. That's the probability that it lies within one standard deviation of the mean. The probability that the sample proportion lies within two standard deviations of the population proportion. Then for C, then we're looking at mu minus 2 sigma which is 2 times 0.1025 from and to 0.7, that works out to be 0.495 and 0.905, which when we relate that to x values is 10 and 18, and so using our binomial distribution again, so I'll change that to a 10 and that to an 18, and we get 0.975. Okay, so those are those values. Okay, so from there, then this is the exercise you could work on for those. Meanwhile, I shall keep going. All right, so then, I won't worry about this, but it might be worthwhile for you to have a look at the yellow text, okay, specifically at this example, just to observe that with a large number for our sample size, the distribution of sample proportions, it does actually approximate a normal distribution. So we've said before that for any given sample, then we're not going to necessarily get it exactly matching the population proportion. But what we would find is that with a large sample size, the distributions of sample proportions are going to match or approximate a normal distribution. So just imagine these are a bunch here, you get a whole large number of samples. This value here right in the middle is actually the population proportion. So on any given sample, you may have a sample proportion being down here. You may have another one up here, but over the long term, you're going to get more that are closer here. They're going to average out to be this population parameter, okay, and it's going to be shaped as a bell curve. So what we can do is use the normal distribution as a means of helping us to determine probabilities when you have a large enough sample size. Okay, so we're going to use that here. Assume that 60% of people have a driver's license. Using the normal approximation, find the approximate probability that in a randomly selected sample of size 200, more than 65% of people have a driver's license. Okay, so what we'll find is that perhaps on a given sample, then maybe there might be some instances where there's only 20% of people have a driver's license. There might also be something like maybe 80% of people have a driver's license. Okay, but in others you might have 40, whatever. But we're going to find that over the long term we should get a normal distribution here, 0.6. Okay, 60%. That's where we have it. That's our on average. So sample size of 200. Okay, we're going to then take our mean at 0.6. Our standard deviation can be found using 0.6 times 0.4 divided by the sample size of 200, which works out to be 0.03464. And then we're wanting to find the probability that more than 65% have a driver's license. In other words, here's 65%, say. We're looking at more than 65%. So we want that probability. What's that area under the curve there? So we're going to use norm CDF, with a lower value equal to 0.65, an upper value of, look, you just choose a very large number. It doesn't really matter. In this case here, you could just, something like 10 is going to be big enough, really. You could put infinity in there if you wanted. It's going to give the same value. And we want our standard deviation at 0.03464, and of course our mean at 0.6. So then when we stick that in the calculator, we're going to find here interactive continuous CDF, lower at 0.65, upper 10, this 0.03464, mean 0.6. Okay, and we get probability at p hat is greater than 0.65 is equal to, what did I say it was? 0.074. Okay, so that's the probability. Okay. Dare say the graph is going to look somewhat different to that. I mean, that's a small, that's like 7.4%. And according to this graph that I've drawn, that's not it. But this is just like an example of what it might be. Obviously, these are very close. The 0.8 must be a lot closer. Okay. Hopefully that makes sense. So exercise 15C, we could do some work on that. All right, now just going to look at confidence intervals. The reason we analyse samples is to make inferences about the population. So a point estimate is where we just take a random sample and find a value for the sample proportion. And we can use that to estimate the population proportion P. But that's just a point estimate, and you would never be very confident that that's actually what the population proportion is. An interval estimate, okay, is much more sensible. It's where you are looking at saying the population proportion may fall between these two values, and we have sort of some level of confidence about that. Okay, so that's just where we need a confidence interval. So we might be, say, 50% confident. Okay, or we might be 90% confident that it lies within values. That's what we're talking about here. Now, we know that for a large sample size n, the sample proportion p hat has an approximately normal distribution, with our mean at p and our standard deviation given by a formula. Now, if we standardise, okay, by bringing everything back to having a mean of 0, okay, that uses this rule here for z, our standard normal value given by x minus mu over sigma, then we can say that the distribution of the random variable z is given by this here. Okay, so this is our x value, that's our mu, our mean, and this is our standard deviation, so that gives us z. So now if we use inverse norm CDF for a central region, so if I go here and I go inverse norm CDF and I change that to center, set my probability at 0.95 because I'm wanting a 95% confidence interval with standard deviation of 1 and a mean of 0 because we're standardizing. That gives us a z value of 1.96. Okay, so for a 95% confidence interval, we're looking at using this z value of 1.96. Okay, so if we apply this value to our distribution of sample proportions, this is our z value. We're wanting our z value to fall between minus 1.96 and positive 1.96 because that'll give us approximately 0.95. by doing a little rearranging here, multiplying through here by our standard deviation. Okay, then we get p hat minus p, being between negative 1.96 times our standard deviation and positive 1.96 times our standard deviation. That's going to be equal to 0.95 approximately. And then if we go a bit further by getting our p on its own, this then is what we end up with. This is the interval for a 95% confidence interval for our population proportion, P. Okay, so then the confidence interval for P is given by P hat, our sample proportion, minus Z times our standard deviation. At the lower end and at our upper end, it's our sample proportion plus Z times the standard deviation. And if we want a 95% confidence interval, then we use a Z value of 1.96. Sometimes we may be asked for a different confidence interval. So for a 90% confidence interval, we just go back here, use this central region. Okay, if you need to go back and check what I did before, then do that. Change that to 0.90. That's 1.64. So for a 90% confidence interval, then our Z value is 1.64. And for a 99% confidence interval, our Z value is 2.58. I'm not going to necessarily remember those values, but it's important to know how to get them. Okay. So we want to find an approximate 95% confidence interval for the population proportion P of primary school children in Australia who regularly use social media. If we select a random sample of 20 children, find the sample proportion to be P hat equaling 0.7. So we want to find a 95% confidence interval. So the way we do that, now since P hat equals 0.7 and N equals 20, then our standard deviation is given by 0.7 times 0.3 divided by 20, and that is equal to 0.1025. Now a 95% confidence interval is equal to P hat minus Z times 0.1025, and at the lower end, at the upper end, it's P hat plus Z times 0.1025. Okay, that's our sigma standard deviation. Okay, which is going to be 0.7 minus 1.96 times 0.1025, which works out to be 0.4991 and 0.9009. So our 95% confidence interval is between 50% and 90%. What does that mean? Basically, that we're 95% confident that P, okay, the proportion of primary school children who regularly use social media is somewhere between 50% and 90%. Okay? Not that's a pretty broad range. But the reason it's so broad is because our sample size is only small. Okay? Okay, so this really is just highlighting what we're dealing with here. Say there's 20 samples here, well there's 20 samples here as an example, pictorially. This is the actual population proportion. Each sample has this range. Okay, this is your lower, this is your upper. Okay, each of these are the confidence intervals, and these red dots represent the actual sample proportion for those particular samples. Now, for all of these, they're all have, except for one, all have within that range our p-value. So that's 95% is 19 out of 20. So 19 out of 20 will contain the population proportion or parameter. Okay. Same thing here, for example 2, except that we've got a sample size of 200. And when we do that, so we've still got our p hat equaling 0.7, n this time is 200. And so our standard deviation is going to be altered slightly, 0.7 times 0.3. Divide that by 200. That gives us 0.0324. So now our 95% confidence interval is equal to 0.7 minus 1.96 times 0.0324 to 0.7 plus 1.96 times 0.0324. So then our confidence interval now is 0.64 to 0.76. So between 64% and 76% is our 95% confidence interval. So you can see it's narrowed down significantly because our sample size is significantly larger than the first time. Okay, then for this one here, out of a sample of 300 components made in a factory, 24 are deemed to be faulty. What is the acceptable proportion of acceptable components? So if 24 are faulty, that means our P hat in this instance is using X over N. It's 276 out of 300, which is 0.92. Determine the 95% confidence interval for selecting an acceptable component and then write a concluding statement. So N equals 300. P hat equals 0.92. Sigma is going to be 0.92 times 0.08 divided by 300. That gives us 0.01566. And it's a 95% confidence interval, so Z equals 1.96. So our 95% confidence interval is equal to 0.92 minus 1.96 times 0.01566 to 0.92 plus 1.96 times 0.01566, which gives us 0.89 to 0.95. So that's our confidence interval between 89 and 95%. So in terms of a concluding statement, we can be 95% confident that between 89% and 95% of components manufactured will be acceptable. Okay, so moving on. When we use confidence intervals in a practical setting, it's more useful to make statements in terms of the distance between the sample proportion, which is the sample estimate, and the endpoints. An example of such a statement would be typically used when taking polls, Okay, we predict the proportion of people who will vote Labor in the next election as 52%, plus or minus 2%. That 2% is what's called the margin of error. So the distance between the sample estimate, in this case 52%, and the endpoints of the confidence interval is the margin of error, which, when we consider what we've just been calculating, for a 95% confidence interval, the margin of error is given by 1.96 times the standard deviation. So we should be able to see that in order to make the margin of error smaller, we need to make the sample size larger. So just kind of quickly going back, because as our n gets bigger, this fraction here gets smaller, which means this overall value for the margin of error will be smaller. So that's really the governing factor that we have for our confidence intervals and our margin of error. So focusing here, then, determining the sample size required to achieve a margin of error of 2% in an approximate 95% confidence interval for the proportion of P of primary school children in Australia who use social media, if the sample proportion P hat is found to be 0.7. Okay, so our margin of error is Z times standard deviation, which is P hat times 1 minus P hat divided by N. Now we're wanting our margin of error to be 2%, so 0.02, with a 95% confidence interval, so Z is 1.96. The sample proportion is 0.7. So we're wanting to solve for n. So working our way towards that, we can divide by 1.96 equal to the square root of, this would be 0.21 over n. So then take square both sides, equal to 0.21 over n. If we solve for n, then that will be equal to 0.21 divided by 0.02 over 1.96 squared, which works out to be 2016.84. So therefore a sample size of 2017 is required. Okay, so really straightforward, but it's worthwhile just paying attention to those sorts of things. Now, from a practical perspective, it's unlikely that we would actually know the value of the sample proportion before we've selected the sample. However, it's usual to use an estimated value based on previous knowledge, okay, or perhaps a pilot study, in order to determine the sample size. And so you can just use that as an estimate so that you have a guideline for selecting, say, the particular sample size that we need. Okay. All right, I just want to look at one more little example, which I'll just add underneath here. Okay. A landscape supplier. Just pause for a moment. Okay, so we've got a landscape supplier is 95% sure that 30% to 40% of shoppers prefer their mulch. What sample size was needed for this confidence interval? If we have the endpoints for our confidence interval, by implication, that means the sample proportion is halfway between it. Okay, so a 30 to 40% confidence interval implies P hat to be equal to 35%, or 0.05 0.35. Okay. So 95% confidence interval. Okay, p hat is 0.35. If our endpoints are 0.3 and 0.4, that means our margin of error is equal to 0.05. Therefore, we can use m being equal to z times p hat times 1 minus p hat over n. So that's 0.05 equal to 1.96. So that's 0.35 times 0.65 over n. And we can go through and solve for n. That would be 350. Solving in the same way as we did the previous one. Okay, so I guess the thing I want to highlight here is that sometimes we are given a confidence interval. And because we're adding and subtracting the same quantity from the sample proportion, we know our sample proportion will be halfway between. Okay, and that's in a variety of kind of questions around this sort of thing. Okay, so hopefully that kind of makes it clear with this particular topic.